Hello, I am Andrew Fastenau, a research associate at the UW-Parkside Applied Physics Laboratory. In collaboration with the work at the Oxide Laboratory of UW-Madison, and under the Weiss's UW Applied Research Grant titled Nanofabrication of SIS Tunneling Josephson Junction Device, here at UW-Parkside Student Showcase, I will detail the theory on Josephson Junction Device, different types of Josephson Junction devices, challenges involved in fabrication of new types of YBCO-based Josephson Junction device, and our novel design to overcome these challenges. Josephson Junction are nanoelectronic devices in scale that consist of two thin layers of superconducting material with insulating material between them, of which electric current flows in the absence of applied electric voltage. When this superconducting material is cooled below the transition temperature, electrostatic interaction between the electrons of said material are overcome by an attractive interaction and form a pair called Cooper pairs, carrying a charge of 2e, the magnitude charge of electrons. Electrons are described by a class of functions known as wave functions, which describe the state of the electron system. Cooper pairs are no different, described by a singular wave function that results in a single phase per superconductor. If the superconductor is interrupted by the inclusion of insulating material, a phase difference of the two superconductors appears. The set of two superconductors in this arrangement is known as two weakly coupled superconductors. Interestingly, if this insulating material is thin enough, the amplitudes of the wave functions penetrate through, allowing the Cooper pairs to tunnel through this insulating material. This tunneling is essential to the weak coupling and is necessary for Josephson junction devices to operate. The uses of Josephson junction devices are many, from superconducting, quantum interference devices, SQUID, biomagnetic sensors used in medical imaging, qubits used in quantum computing, rapid single flux quantum circuits, to terahertz frequency detectors. Other uses involve geophysical measurements, NASA instrumentation, and military defense applications. Many types of Josephson junction devices exist, from point contact, microbridge, thin film tunnel junction, bicrystal, grain boundary, and ramp edge. The major limit use of these Josephson junction devices is that these junctions are below low transition temperature, demanding a form of very expensive liquid helium-based rigorous refrigeration system. The development of well-controlled and reproducible junction device has proved challenging, as the thickness of the insulating material in the junction must only be about a nanometer thick. It must provide high potential barrier to produce enough phase difference. Other challenges consist of finding the electrical insulator with high electrical resistivity, high critical current values, and the transition temperature having a temperature above that of the boiling point of liquid nitrogen. The conventional design of the junction includes contact type, step edge, ramp type, and grain boundary, with them posing insufficient critical current or too low transition temperature. We, here at the UW-Parkside Applied Physics Lab, have developed a novel electrical insulator called PBCGO and YBCO-based new SIS sandwich type design to meet all these requirements. Our proposed Josephson junction may have high critical current and normal resistance and advantage of high critical temperature superconductor-based Josephson junction device. We have already fabricated YBCO, PBCOGO, SI bilayer, and have been in the final stages of fabricating YBCO-based SIS sandwich type Josephson junction device. Thank you for coming here today, and thank you for hearing about our research here at UW-Parkside.